Why do some chemical reactions release heat when some chemical reactions absorb heat? That's today's topic on thermochemistry. So let's dive right into it and talk about what the definition of thermochemistry is here. And if we were to look at the makeup of this word thermo is going to talk about heat, and chemistry, of course, is, as we've talked about before, is changes of matter and the interactions that occur with them. So what we have with thermochemistry is we're going to have heat changes that occur during a chemical reaction. You may have noticed in lab, sometimes we mix chemicals together and suddenly the beaker feels hot, or maybe it feels cold. That would be an example of thermochemistry. Also, lighting a Bunsen burner and having it heat up anything, a beaker of some solution, that would also be considered thermochemistry, as we're changing heat and things like that. So let's talk about heat really quickly here and define it. Heat is going to be, we're going to use this symbol lowercase q for heat, and it's going to be energy. Heat is energy, has the ability to do work that transfers from one object to another object due to differences in temperature. So we did talk about temperature, how we can measure the average kinetic energy of several molecules, and that would be its temperature. So let's give you an example of heat transfer from two objects that have differing temperatures. So imagine, if you will, we've got an aluminum block, and we have one aluminum block. We'll draw an aluminum block here, piece of metal made out of aluminum. And let's say this aluminum block has been kept in a freezer, and this aluminum block is, we'll say it's at 0 degrees Celsius. So 0 degrees Celsius. So it's been in a freezer. Now, that's going to slow down, of course, its molecular motion just a little bit, but it's not going to change the phase of the aluminum block. It's still going to be solid aluminum. No big deal. Okay, and then what we have is we have another aluminum block that has been placed in some boiling water, and let's say it's sat in that boiling water for, I don't know, 10-15 minutes, and it's at the same temperature water's boiling. And so water here in Atwater is boiling at 100 degrees Celsius. Okay, now let's say this aluminum block, both of these aluminum blocks are exactly the same. They both have the same exact mass, same shape, everything. The only differences between these aluminum blocks is one is at 0 and one is at 100. Now, what's going to happen is, if we can place these aluminum blocks right next to each other, bottom up, right next to each other so they can touch, what is going to happen is we're going to have a transfer of heat. And as you can predict, the heat will transfer from the hot aluminum block to the cold aluminum block. And that is the way heat transfers. Heat always transfers from hot to cold. It doesn't go the other way around. Now, as you can predict, that the temperature of the aluminum block on the left is going to increase. So this aluminum block is going to increase in temperature as the heat is transferred, and this aluminum block on the right, the temperature is going to decrease. And I bet you could make a prediction about where they're going to end up. And if you would make a prediction, we would guess that the transfer of heat would probably stop somewhere around 50 degrees Celsius. Now, that doesn't mean they'll stay at 50 degrees Celsius, because there'll be further heat loss to the bench that they're sitting on and the air around them, and we'll talk about that in a moment here. So just remember that heat is always going to transfer from hot to cold. We do not put cold into something. We just remove the heat from it, and the molecules slow down. Slow down. That means the temperature is going to drop. Now, in our chemical reactions that we're going to be talking about, they are most likely going to involve absorbing heat, or chemical reactions will release heat. So absorbing is heat coming in, releasing heat, obviously heat is going to be released out. So we have to define what we're looking at here before we dive more into these two ideas of absorption of heat and release of heat. So let's define a couple terms here. And the terms that we need to define are a system. And this is what we are going to focus our attention on, okay, what we're focusing our attention on. So typically in chemistry, the system that we're focusing our attention on are going to be, let's say, a solution in a beaker. It might be a solution in a test tube, or something like that. That's going to be what we are focusing our attention on in chemistry most of the time. And then the surroundings The surroundings are everything around the system. So let's say if we have, scroll down here a little bit, let's say we have a beaker. I'm going to draw one even though I have a picture down below of a beaker. This is going to be our system. And everything around it, the air is going to be considered surroundings. And this beaker, of course, cannot float in midair. So let's say it's going to be sitting on a lab bench. That would also be considered our surroundings as well. So the air and the beaker, everything like that. So what's going on here is we're going to have a transfer of energy, and the energy or the heat can transfer either out towards the air and heat up the air, or heat up the bench, and we see that sometimes, or it can transfer in, and that's what we're going to define now. So here's our very first example, and what we're going to talk about here is we're going to talk about what are called exothermic chemical reactions. Exothermic reaction. Now, what happens in an exothermic chemical reaction is when we have a reaction that is going to release heat to the surroundings. So let's say we have a beaker of, let's just plain water, and into this water we were going to add something. So let's pretend into this beaker here we're going to add some solid sodium hydroxide. Now what happens is when you add solid sodium hydroxide to a beaker of water, the temperature is going to increase. The temperature goes up. The ionization of the molecules, the sodium and the hydroxide ions, ionize, and we're going to start releasing heat. This would be an example of an exothermic process. Now, exo meaning out, thermic meaning temperature, so temperature going out. So if we were to hold this beaker in our hand, we would feel that it was starting to warm up. And if we put too much sodium hydroxide in it could actually become very uncomfortable. So this is an example of an exothermic process. Okay, another example of an exothermic process would be just lighting a match. Lighting a match, it releases heat. Obviously, that's what we use matches to start fires, releasing heat. And I want to give you an example of this. I did find a really neat video. It's going to show you what it looks like when a match is lit in slow motion. Okay, so this is a match head that has been magnified using a macro lens, and then it's also being filmed in very, very, very slow motion. So it's kind of neat. You can see, and you know how when you do strike a match, how fast that match flares up and burns out. This is in slow motion, and this is the guy right here who's done this. And this is what it looks like in slow motion. All the chemical reaction that's occurring in that match, instantly releasing lots and lots and lots of heat. It's kind of neat looking. And this goes on for another 5 seconds. It's if you want to see some other things that they do, the YouTube website is called Ultra Slow Motion, and they do some other things in slow motion that are really, really neat. But you can see this is kind of cool looking too. Okay, the next type of reaction I want to talk about is called an endothermic reaction. Now, endo is going to mean in. So these are reactions or processes that absorb heat. So a great example of an endothermic process or reaction is if we have a cold, one of these cold packs. Now, typically these cold packs, and we're just going to ignore the hot side of this, but let's say we have a cold pack. Some of the cold packs inside will have a small bladder of some sort of chemical, and it's usually ammonium nitrate. And then surrounding that is just typically a solution of water. And so the way that you activate these is you break the ammonium nitrate and allow it to go out into solution, and then it ionizes into the ammonium ion and the nitrate ion. Now, in that process, it is an endothermic process, and it starts absorbing heat as it does this. Now, this absorption of heat, when you put it on your body, the temperature of your body is about 37 37 degrees Celsius, also about 98.6 degrees Fahrenheit. And so this, because the pack is cold, it absorbs heat from your body. And oftentimes people will put a cold pack on somewhere that you've injured yourself. Maybe you've twisted your ankle or something like this, and there's some swelling going on. You put a cold pack on it to actually take some of that swelling down. So this is a good example of an endothermic process. Okay, the last thing we're going to talk about today is thermochemical equations. Now, thermo, again, we're talking about heat changes, chemical equations. So let's talk about the difference between an exothermic and an endothermic chemical equation. And so in this case, we're going to start off with an exothermic. Remember, an exothermic means heat is released. So the breaking of bonds, remaking of bonds, are going to have a release of heat to the environment, and so or to the surroundings rather. And so we have here methane reacting with oxygen to form carbon dioxide and water, our typical combustion chemical reaction. Now, there's a couple of different ways we can illustrate that heat is being released in this chemical reaction. One of the ways we can do this is we can add the word heat to the product side. If we put the heat on the product side, that tells us heat is being released. We can also actually put in the value of the heat. And so for every 1 mole of methane that's being released, we could also have our actual 890 kilojoules being released. So that might replace the word heat right here. Now, something to keep in mind is when we talk about the release of heat, we say that the value of Q, which is our heat, is negative because heat is being released. That's why we make it negative. So sometimes we'll say a chemical reaction where it doesn't actually incorporate into the reaction. They might just say Q is negative 890 kilojoules. That might be written somewhere down below the reaction, and that lets us know that negative value lets us know this is an exothermic reaction. Heat's being released. Okay, and also just real careful, it is on the product side. Now, what happens with an endothermic reaction? Endothermic reactions, again, are going to absorb heat, which causes the reaction to proceed. And in this case, we have calcium carbonate decomposing into calcium oxide and carbon dioxide gas. And so what happens here is a couple ways that we can show this. Oops, let's tab it out a little bit like that. We're going to actually put our heat on the reactant side. So maybe we write the word heat, or maybe we actually punch in the actual numerical values. In endothermic reactions, the value of Q is positive. It's positive. So maybe it says Q is equal to positive and whatever the value is in kilojoules. I don't have that value right in front of me right now. Actually, I can look it up real fast. Let's do that. And that value is 178 kilojoules per mole. And so that positive value, again, tells us this is an endothermic chemical reaction. It's going to absorb heat in order for the chemical reaction to occur. And that is our talk today about heat. Once again, remember, heat is always transferred from hot to cold. Okay. Remember that we can either absorb heat or release heat. Heat, this value which we represent as Q, can be exothermic, which is a release of heat, or endothermic, which is an absorption of heat. Remember, exothermic reactions have the heat value as a product, and endothermic reactions have the heat illustrated as a reactant.